Yeah, yeah. So welcome everyone to the evening session of the school. Professor Eric Poisson will continue with his lecture on black hole perturbations, discussing the perturbations of Schwarzschild black hole. So, Professor Poisson.
Okay, thank you and welcome back, everybody. So yesterday I talked about the underlying principles and the basic methods of perturbation theory, and then we went a little bit into the general relativity aspects of this, talk about the formulation of perturbation theory for that case, and we talked in the end about the geometry of a perturbation of a space-time. And now I really want to apply all of this, but do something much more concrete. So we'll talk for most of this lecture about perturbations of a Schwarzschild black hole. Then I'll move on and say, have a very brief discussion of what is needed when you want to generalize this from Schwarzschild to Kerr. And then at the end, I'll talk a little bit about the practicum, which will be what you will be doing tomorrow. All right, so the literature on perturbations of a Schwarzschild black hole is pretty large, and there's a lot to cover. And I could have talked about all sorts of practical applications of this, but I thought that to keep the discussion circumscribed in a way and sort of not spilling in all directions, I thought that to provide context for the discussion, I would think of the following problem. So suppose that you have a Schwarzschild black hole and it's big, and suppose that you have a body orbiting around it. So, concretely, you can think of a supermassive black hole at the core of a galaxy, and you can think of a 10 solar mass black hole, going around it. So this is a situation where we have a large ratio between the big mass and the small mass. And that's the kind of thing that, as discussed, we need to establish a perturbation theory where the dominant part of the space-time is going to be given by the Schwarzschild solution, but the particle going around it, the black hole going around it, is adding a perturbation to it. So what I'm plotting here is the well-known effective potential for geodesic motion in Schwarzschild. I'm talking here about a generic orbit that would be typically eccentric, would oscillate between an inner radius here, an outer radius here. And for this particular orbit, with this particular value for the energy and angular momentum, we would have an orbit that looks like this. So the object creates a perturbation, and one thing you might want to study about this is the gravitational waves that are emitted by the body, which is just one aspect of the perturbation, which is revealed at infinity. So in principle, we can calculate the perturbation everywhere in space-time, everywhere on top of the Schwarzschild metric. But if we look at that perturbation all the way out to infinity, well, part of that perturbation will reveal itself as a gravitational wave through the two usual modes of polarization of the gravitational wave. And if I were to plot those modes of polarization, well, they might look something like this. So one feature of the gravitational wave is that, well, it has a large amplitude and very rapid oscillations over here, and a smaller amplitude and slower oscillations over here. And the cycle repeats over and over again. And those features of the gravitational wave are directly connected to the features of the motion. When the motion is near the black hole, like this, it occurs, it goes very fast. So, and because of that, the gravitational wave tends to be strong, and the gravitational waves tend to be rapid because the orbital motion proceeds rapidly when the object is close to the black hole. When it comes out and it goes, toward the outer radius over here, in the outskirts of the system like this, the motion is slower, and that translates into those gravitational waves with a lower frequency and a lower amplitude. So, part of the game with gravitational wave astronomy is to start from gravitational wave observations and try to say something about the source. And here you can say that, if we were to observe a waveform that looks like this, we would be able to say something very precise about the nature of the motion. So that's one of the goals of perturbation theory, is to make that connection between what is happening at the source and relate it to what is happening, what is revealed in the gravitational wave signal. So that's the context I want to consider here. All right, so how do we start? Well, we begin with a Schwarzschild, space-time. So we begin with an unperturbed Schwarzschild black hole. So that would be the lambda equals 0 description of the space-time, and that's given by the well-known Schwarzschild solution. And
So,
now
there was a
yeah,
question, a
yeah.
clarification required, I guess. What is new on the y-axis in the previous?
Oh, that's the effective potential for geodesic motion in the Schwarzschild space-time. So it's the effective potential. That's my notation for it.
Okay, I think it
Okay.
is.
Yeah,
Thanks.
good. Thanks for asking to clarify. Okay, so we start with the space-time, and now we place this extra body in the space-time. It has a mass m, and at this level of description, I can consider the body to be moving on a geodesic of the Schwarzschild space-time. And that has to do with the fact that when we work to first order in perturbation theory, the energy momentum tensor is constructed from the background metric, and its conservation identities are going to be formulated in the background metric. And those conservation identities predict that the motion will be geodesic in the background spacetime. So consistently at first order in perturbation theory, I can take the body to move on a geodesic of the background spacetime. In fact, I must do that. And here we can think of the energy momentum tensor of the body as being that of a point mass. So I'm modeling the extra body as a point mass in the Schwarzschild spacetime, and I can describe it as a delta function. So those are little technical details that are not important for most of the discussion, but that's something maybe to keep in mind. So as we discussed last time, we can introduce the first order perturbation of that spacetime as the first derivative with respect to lambda of the one parameter family of metrics that we construct in perturbation theory. And that would be the first derivative evaluated at lambda equals 0. We do that. As discussed, we also need to impose a coordinate condition that will restrict for us the freedom that we have in making identifications between the background spacetime and the perturbed spacetime. So that is something that needs to be done. And when we do all of this, well, we end up with a concrete version of this equation over here that says that the first order Einstein tensor calculated from the background metric and the perturbation is going to be equal to the energy momentum tensor of our point mass. And the structure of this equation here is that we have a linear differential operator acting on the perturbation. The differential operator is constructed from the metric and all of its associated quantities like Christoffel symbols and Riemann tensor and all of that. I don't want to go into the detailed description of this because that's going to be part of the practicum tomorrow. So in principle, we can calculate the perturbation everywhere in space-time. We can look at it close to the particle. We can look at it close to the horizon. We can see what enters the horizon. And we can look at what goes out to infinity. And as I said, part of what goes out at infinity is going to be in the form of gravitational waves. And that's the type of thing that we would like to extract from our calculation. Okay. Now, to turn those ideas into a practical calculation requires a lot of details. And that's where all the hard work needs to go, really, to implement all of those details and make sure that things are done in the best way. And what I mean by the best way is that, well, in this case, because we have a background spacetime that has a high degree of symmetry, and here I'm insisting mostly on the spherical symmetry of the spacetime, but I could also talk about the fact that the background spacetime is static. That's another symmetry that I can rely on. And the reason why this is important is that we can rely on the symmetries of the background spacetime to introduce a decomposition of the variables into basis functions that incorporate the symmetry. And that basically means that we have a nice packaging of all those perturbation variables that is optimum because we have made maximal use of the underlying symmetries. So that's always something that we do in physics. We try to rely as much as possible on symmetry to help us with the calculation. So the technical difficulties that we face when we do this is that we're not dealing just with scalar quantities here. If we were dealing with just a scalar quantity, we would know how to decompose that in scalar spherical harmonics, the familiar functions that we first encounter in quantum mechanics. They can be made use of here. And we know all about expanding scalar functions in scalar harmonics. Part of the technical challenge and is the fact that we're not dealing with scalars, we're dealing with a tensor in spacetime. And that means that we have to consider constructing a basis of tensor spherical harmonics. And that's a little bit vexing. There's a ton of details that go into that that are not really essential. They're not that important, really. They're not, fundamental to anything. It's just that in order to carry out with a calculation and to be able to do anything in practice, those are details we have to go through. And it's kind of vexing because when you look at the literature on this, there are tons of different conventions on the construction of tensor spherical harmonics. And different authors use different conventions, and sometimes to go back and forth between different notations can be, time consuming and tedious and, irritating. So, so that's just the fact of life. Unfortunately, we have to live with this. And it's part of the story that every author thinks that they've got the best convention for this business, the best conventions to define tensor spherical harmonics, when all of those people should know that my convention, mine, is the best. So we all think that. We all think that ours is the best, and no one can agree on, on anything. So that's just something that you have to navigate when you navigate through this literature. Anyway, let me give you my my perspective on this. And I'm afraid that the next few slides are going to be a little bit technical in that sense, but I just wanted to give you, a flavor of what it means to really deal with those details when you're trying to expand a tensor in spherical harmonics. All right, so let's think first of doing it with a vector. So when we're doing it with a scalar function, the only thing that we have to worry about is to construct a functional basis, and that's what the spherical harmonics are. And there are theorems that tell us that if we expand a function in a function on the sphere, a function of theta and phi, we can always do it in terms of spherical harmonics because that set is complete. So we can always decompose a function in terms of spherical harmonics, and there's a one-to-one association between the function and the coefficients that enter here into the decomposition. So that's all fine and good. When we try to generalize this from scalars to vectors, well, we still have the functional basis to worry about, but on top of this, we have to construct a vector basis, which means that we need three members of the basis to reflect the three directions of our vectors. So here I'm thinking of flat space, I'm thinking of three-dimensional space, and I'm thinking of decomposing a three-dimensional vector in that depends on the two positions on the sphere. So that's what I'm talking about here. We'll talk about four-dimensional things in just a moment. So how do I go from a functional basis to a vector basis? Well, you just have to identify three vector directions. And if we're working in spherical coordinates, well, we have a vector that points in the radial direction, we have a vector that points in the theta direction, and we have a vector that points in the phi direction. So we can use those vectors as a means to construct a basis. So how do we do it in practice? Well, we say that the first member of the vector basis is going to be just our spherical harmonics multiplying the radial vector that points away from the sphere. So we get one vector direction, that's the first member of our basis. To get the two other members, we have to consider orthogonal directions. So now we have to consider the theta and phi directions, which are tangent to the sphere. And one way of doing it, which is kind of nice and works well in terms of the mathematics, is for the second member to be defined as the gradient of our spherical harmonic functions. When I take the gradient, I will generate either a theta derivative or a phi derivative. The theta derivative will be directed in the theta direction. Same for the phi derivative, it will be directed in the phi direction. And because the YLMs depend only on theta and phi, I know that the gradient will be purely tangent to the sphere. They will point necessarily orthogonally to the radial direction, either in phi or theta. So now I have two members of my basis. I need a third member, and the requirement for the third member is that it has to be orthogonal to the previous two. So it has to be orthogonal to this vector, it has to be orthogonal to that vector. And a quick way to achieve this is to just take the cross product between the radial vector r and the gradient vector. The cross product will be orthogonal to both, and therefore it will be orthogonal to the first two members of the basis. And if you do the calculation, you'll find that, well, the cross product here gives you a phi derivative in the direction of theta and a theta derivative in the direction of phi. I'm being a little bit schematic here. You shouldn't take those equations at face value. There are factors of sine theta and that should be inserted here to make things exactly right. But I want to focus on the ideas. So that's how you go from a scalar basis to a vector basis, and you basically rely on all of those basic directions that are defined by the radial vector and the theta and phi vectors. One observation here before we move on is that because I'm constructing Y3 here as a cross product, this construction is not defining an actual vector, it's defining what's known as either an axial vector or a pseudo vector, and that has to do with the behavior of vectors under parity transformations. It's something that needs to be understood when you go into the details of this. So those two vectors have, this is an actual vector, this is an axial vector, and they have different properties under parity transformation. That's something to to sort of be aware of. That's part of the story when we go from scalar to vector to eventually tensor. Okay, so let's move on from here. What I'm going to do here is to introduce a notation a bit more explicitly that distinguishes between the radial direction and the angular direction. So because I'm really focusing on the spherical symmetry of the Schwarzschild spacetime, or I will move to that in a minute. So I really want to distinguish the sphere from the remaining part of the spacetime, which lies in the t and r directions. So I'm going to segregate my my indices here. I'm going to distinguish explicitly between what is a radial direction, eventually a time direction, versus what are angular directions, and I'll collectively denote them by this capital index A. And when I consider operations on the sphere, when I consider the sphere to be the distinguished space here, mathematically speaking, I will refer to this as a scalar as far as the sphere is concerned, and I will refer to this as a vector as far as the sphere is concerned. Yeah.
Yeah, so in the previous slide, I think this axial vector also turns out to be tangential to the surface. Is it right?
Oh yeah, because it lies in the theta and phi direction. It's orthogonal to the radial direction, and therefore it is also tangent to the sphere.
Okay, thanks.
Yep, good, thank you. All right, so just a slight change of point of view here. I will consider this to be a vector and this to be a scalar. And this makes sense so long as I focus on operations on the sphere. So I'm thinking of the sphere as the distinguished part of the space here. So when I decompose a scalar, like the radial component of my vector, I am doing it as a scalar expansion purely in terms of scalar harmonics. When I decompose a vector on the sphere, then I will do it according to the vector basis that I just constructed. But now my vector basis is two-dimensional because, again, I focus on the directions defined on the sphere only. And here I distinguish between the gradient construction that I had defined previously. That's the YA that we have here. And the XA that I defined here is basically, well, the cross product construction that I had previously, except that I'm re-expressing it slightly differently in terms of the permutation tensor defined purely on the sphere. So this is just a small step on top of what we did previously, a small change of attitude where I really focus on the spherical directions, distinguish them from the other directions that we might have in our space-time, and I introduced, therefore, a two-dimensional point of view on vectors and eventually on tensors. And because of that two-dimensional point of view, I will introduce a two-dimensional basis for my vector harmonics on the sphere, the one corresponding to the pure vector and the one corresponding to the axial vector construction as seen previously, but re-expressed slightly differently. So nothing to worry about. That's the same thing, but packaged a little bit differently. Okay, so that's going from scalar to vector. Now let's do the next step and moving to tensors. And I'm still going to think of this in terms of three-dimensional space, and we'll add the time component to that in a moment. So suppose that we still work in three-dimensional space. I'm going to continue to distinguish between the radial direction and the angular directions. And if we're dealing with a tensor, now we have possibilities of having indices purely in the radial direction, or partly in the radial direction and partly in the angular directions, or fully in the angular directions. For simplicity here, I'm going to focus on symmetric tensors. I could generalize this to any type of tensor. I could just include a discussion on antisymmetric tensors, then I can combine the two. But, because eventually I'm going to apply this to the metric being symmetric means that I don't lose anything for this discussion if I focus entirely on symmetric tensors. So the idea here is that because I've distinguished the radial direction from the angular directions, anything that comes with two radial indices here can be considered to be a scalar. Anything that comes with a single angular index, A, can be considered to be a vector on the sphere. And anything that comes with two angular indices, well, can be considered to be a symmetric tensor on the sphere. So that, again, is going to be my point of view where I really distinguish the sphere from all the other directions. Okay. Whenever we're dealing with tensors, it's always a good idea, or it's usually a very good idea, to decompose them into their smallest pieces. So if you were given a general tensor, the first thing you would want to do is to decompose it into symmetric and antisymmetric pieces. Here we don't have an antisymmetric piece, so let's focus on the symmetric tensor. The next thing you would want to do for that symmetric piece of a tensor is to decompose it into a trace part and a trace-free part. And that's what I'm doing here. I'm saying that VAB can always be expressed in terms of something proportional to the metric. Omega AB here is my notation for the metric on the two-sphere. And more precisely, I'm talking about the metric on the unit two-sphere. So the metric on the unit two-sphere is familiar to you. It's the usual d theta squared plus sine squared theta d phi squared. I can re-express this in index form by introducing this metric tensor on the two-sphere, and that's my notation over here. So what I'm saying here is that I can always decompose a symmetric tensor on the sphere into a piece that's going to be proportional to the metric and an extra piece. That will be called the trace part of the tensor. That will be called the trace-free part of the tensor. And the way to define the trace here will be to multiply the tensor with the inverse to that metric. So this is the metric on the sphere. This is the inverse metric on the sphere. And by definition, according to this this attitude that we have where we distinguish the sphere above everything else, calculating the trace of a tensor will just be multiplying the tensor with the inverse metric. And you can quickly go through the calculation here. If you multiply the left-hand side with the inverse omega, you will multiply omega with its inverse. That defines the unit matrix. You take the trace of this, you get 2 because it's a 2-dimensional metric. The 2 cancels out the factor of 1/2 and you get V. That term over here is trace-free in the sense that the same operation here acting on V hat would return 0. When you work out the number of components, any symmetric matrix in 2 dimensions will have 3 independent components, one of which is going to be the trace. That's going to be the sum of the diagonal components. And then you have 2 remaining components off diagonal, and that's the trace-free part of the tensor. So that's what I'm doing here. So I'm introducing this kind of decomposition of quantities on the sphere, so scalar, vector, tensor, and then I'm decomposing the tensor into a trace-free part, which is going to be another scalar, and then a true tensor that will be by definition trace-free. And once I've done that, I've basically decomposed everything into the smallest pieces possible. And typically we talk about irreducible pieces and things that transform accordingly under the representations of the rotation group. There's a whole mathematical language that goes into that, but no need to get bogged down with details like this. Okay, the next ingredient I'm going to need here, I've introduced the geometrical ingredients on the sphere, like the metric. Let me finish the thought. I've introduced the geometrical ingredients on the sphere, the metric, the inverse metric. I could define the Christoffel symbols. I could introduce the Riemann tensor on the sphere. I could do all of those things, and typically we do that in calculations. But one thing that I'll need explicitly here is the covariant derivative defined purely on the sphere. And basically think of this as the covariant derivative that we define with respect to the Christoffel symbols we would calculate on the basis of this 2-dimensional metric defined here. So that's a covariant derivative that will be acting on spherical tensors or spherical vectors such as these over here. I see that there's a question.
Hi, I was just wondering whether the vector can also be decomposed in terms of a scalar and divergence of a scalar, and similarly the tensor may be able to written as one could write it as a product of vectors. Those are not possible in these cases.
Okay, so let's talk about vectors. So you're saying that this vector could be defined as what?
Of a scalar.
So in a sense, that's what I'm, let's see. So in a sense, so yesterday you were asking about this decomposition that we find in perturbations of cosmological spacetimes, where we decompose into scalar, vector, and tensors.
Right.
So in a sense, it's not quite the same language I'm using, but there's a relationship. So in that language that people use typically in cosmology, they would say that this is the scalar part of the vector perturbation, and this would be the vector part of the vector perturbation. So in that sense, I'm doing the same thing, except that I'm describing it differently. And here, instead of describing this as a scalar because it's created from a scalar by applying a gradient, whereas this is something different. So the language used is slightly different, but it achieves the same thing. And when I do it for tensors, you'll see it on the next slide. There's also, you can also look at the tensor as being made up of, scalar part, vector part, tensor part. It's just that I'm using a different language and doing something equivalent, but described differently.
I understand. Thank you.
Okay, good. Yeah, so those are little subtleties that that require some translation between languages used in different contexts. So yeah, it can be a little bit confusing. But yeah, thanks for asking, and that allowed me to go back to that question you asked yesterday.
I have a small question.
Yep.
So we are basically decomposing the perturbations into this scalar, vector, and tensor parts, right?
Yep.
So how do we know that we can decompose the perturbations into this scalar sector and a vector sector and a tensor part? And related to this, this looks very similar to how one derives the Regge-Wheeler equation. So in connection to what we do when we study quasi-normal modes, can we also not just simply take a field, say a scalar field, and write down the Klein-Gordon equation like we do when we do quasi-normal mode analysis, instead of going down this route of studying the perturbations so explicitly?
Okay, so two questions. So the first question was, how do we know that we can do this decomposition into scalar, scalar, vector, and tensors? Well, so the argument there is simply that you need to make sure that the basis you construct, this functional and tensorial basis that you construct, you need to show that it's complete. And I won't show completeness here, but there's a mathematical strategy to prove completeness of the decomposition. And the statement is that, well, you can prove that the decomposition is complete, and therefore that the decomposition can be, done on any tensor, that lives in space like this. So here the context is still three-dimensional tensorial quantities, and the statement is that you can always accomplish this decomposition in terms of the pieces that I'm describing. But I won't prove that. You'll have to take my word for it. The second part of the question had to do with why not just do a Klein-Gordon perturbation? And of course, the answer is that you can do that if you wanted to consider a scalar field as a source of perturbation. Sorry, let me say this differently. If you wanted to put a scalar field on top of the Schwarzschild spacetime and work out the physics of that scalar field in that fixed background spacetime, you could of course do this, and you would formulate a Klein-Gordon equation in the curved spacetime of the Schwarzschild black hole. And you would apply all of those tricks, except that because you're working on a scalar field, the functional, there's no need for a decomposition in terms of scalar vector tensors. The only thing you have is a scalar field. Therefore, the only decomposition you need is that functional decomposition in spherical harmonics. So of course you can do that. And usually that's the first thing that you should do, because it's a simpler problem than doing a metric perturbation. But if you want to do a metric perturbation, if you want to really consider a gravitational perturbation of the Schwarzschild black hole, then, well, you cannot escape the fact that you're dealing with a tensor, and that a tensor really needs to be decomposed along the lines that I'm describing here. Does that answer your question?
Yes, thank you.
Okay, very good. Okay, so now let me do the rest of it. So we have the scalar part and we have the vector part, under control. So now we just need to, go the next step and to take our, to take our vector here. Sorry, to take the tensor, to take the spherical part. I'm having trouble speaking. So this is the scalar, this is the vector. Now this is going to be the tensor on the sphere, and we want to decompose that into spherical harmonics, and I'm going to do it in, this way. So first, I'm introducing the part of the tensor that's going to be proportional to the metric. That is a scalar, that's the trace part, that's a scalar, and that scalar can be expanded in spherical harmonics, straight spherical harmonics. So that's what I'm doing here. So the little v here that I defined here, I can straightforwardly expand that in spherical harmonics. So that's my first term over here. Then I have the remaining part, which is going to be the trace-free part of the tensor. And that I can decompose into a tensorial basis, a tensorial spherical harmonic basis, that will have this property that is going to be trace-free in the spherical indices AB. So I have two of those. I have a y and I have an x. The y is defined in this way through two derivatives of the spherical harmonics. So remember, we started with the spherical harmonics, and to define a vectorial basis, the first thing we did was to take a gradient, so one derivative. If I want to move on and define a tensor basis, well, it's natural to expect that I could achieve this by taking two gradients, two derivatives. That's what I have here. And those are covariant derivatives on the sphere. That is not trace-free. I can make it trace-free by adding a term proportional to the metric. And if you were to take the trace of this, by multiplying by the inverse omega metric, you would find that, this would define the Laplace operator on the sphere. This would produce L plus 1 times y. You would get rid of this with the factor of 1/2. And that would be the equation for spherical harmonics, the eigenvalue equation for spherical harmonics. If you didn't quite see that, no worries. All I'm saying here is that I can construct a trace-free tensorial basis of spherical harmonics by taking two gradients and then making sure that I take out the trace to make the result trace-free. So that's one way to achieve this. The other way to achieve this would be to take the previous axial vector that we had, the x vector that we had before, defined in this way through the permutation symbol, and I can take an extra derivative of this. And that's what I'm doing here. Then I'm symmetrizing the operation. And then in principle, I should have to remove a trace, but you can prove that this is trace-free, and therefore you don't have to worry about, an extra trace piece. So all I'm saying here is that except for, little technical complications, you achieve the tensorial basis by going through the same operations as for the vector basis. And essentially, the key piece is to take extra derivatives. One derivative for the vector, two derivatives for the tensor, and you just make sure that everything works out according to the rules, which means everything's symmetric and trace-free, and a good, classification under parity transformation. So this behaves as a genuine tensor, this behaves as an axial tensor. It has the same sort of character as the axial vector we had in the vector case. Once we have this, we have a complete decomposition of our, three-dimensional tensor into spherical harmonics, vector harmonics, and tensor harmonics. And just to go back to the previous question, so this, and this would be considered to be scalar perturbations in the sort of cosmological type language. This would be considered to be a vector perturbation in that language, and this here would be considered to be a tensor perturbation in that language. Okay, so that's what we would do in three-dimensional space. To generalize to 4 space-time dimensions, well, doesn't require any more to it. So we just add one dimension, but that dimension is time, and time is just one extra dimension on top of the spherical dimensions. So all this, all this means that there's nothing more to the new dimension than what we had before. So what I'm trying to say here is that anything that doesn't have an angular index, like, the time radial component of my metric tensor, my metric perturbation tensor, all of those things here will behave as a scalar on the sphere. So I'm working on the sphere. Anything that has a mixed components like this, t theta, t phi, r theta, r phi, because there's only one angular component, that will behave as a vector on the sphere. And then anything that has to do with two angular components will behave as a tensor. Anything that's a scalar, I can expand in scalar harmonics. Anything that's a vector, I decompose again in vector harmonics, the true vector, the axial vector. And anything that's a tensor, I decompose as I did before in terms of a trace part and two trace-free parts, one involving a true tensor, the other one involving an axial tensor. So what I'm doing here is introduce a decomposition in scalar vector tensor harmonics of the metric perturbation, and I'm calling it, I'm calling that perturbation P alpha beta, and then I'm just distinguishing what is an angular index and what is not an angular index. The capital indices are going to be angular indices. The lowercase letters here are going to be non-angular indices. So basically, those are indices that span the time direction and the radial direction. The coefficients that I introduce in front of the spherical harmonics are going to be my reduced perturbation variables. They're going to be what remains after I've decomposed everything in spherical harmonics. And I'm going to have one such quantity per Lm, because, of course, that's the functional aspect of the decomposition. So we get an infinite summation over all values of L and M as we expand in spherical harmonics. So the coefficient here I call H, the coefficient here I call J, another H with just one index. And here, for just conventional reasons, I factor out a factor of R squared. The trace-free part is going to be called K. The symmetric trace-free part is going to be a G. And over here in front of the X, that's going to be called H2. And for, again, historical conventional reasons, there's no R squared being factored here. None of that is important. What's important is that we have a complete decomposition. We have a unique one-to-one correspondence between each one of those coefficients and the metric perturbation. So we can always extract any one of those by taking appropriate projections, and we can always reconstruct any perturbation through, in principle, an infinite sum over spherical harmonics. In practice, it tends to be the case that the sum converges fairly rapidly. If you're dealing with smooth perturbations on the sphere, you get exponential convergence in the spherical harmonic decomposition. So in practical applications of this, typically you include a handful of L's, a handful of M's, and you have a perfectly fine representation for the complete perturbation. So the reason why this is done is not just because it's mathematically convenient to do this decomposition, but also it's very practical, because in practice, those infinite sums can be truncated very quickly, and you get very fine answers by including just a finite, small finite number of terms. Okay, I think it's probably a good time to pause a little bit and ask if there are questions.
So are there any questions? Professor Poisson, I actually had a question. It's just a repetition, just a clarification.
Yep.
When you say vector here, like that's the second expansion, P with a Latin A and a capital V, yes. The first term there is actually a scalar perturbation if you use the cosmology kind of language. Is that you were just mentioning? Because it's derived from a gradient or something like that?
That's right. So in their language, anything that's generated by a gradient of a spherical harmonic, a straightforward derivative of a spherical harmonic, that would be considered to be part of the scalar sector of the perturbation.
Right.
Anything that's generated through an axial vector or an axial tensor would be either a vector or a tensor. So in that language, this is scalar, this is scalar, this is scalar, this is scalar, this is vector, this is tensor. So it's not quite this, because they're working, so their decomposition is three-dimensional as opposed to being two-dimensional as we do it here. So so their derivative operations are three-dimensional, not two-dimensional, but in spirit it's like that. Yeah.
And one more quick question. It may not be directly relevant for this, but is there any connection with this decomposition and the fact that there is a killing tensor also, which uh, exists in, say, Schwarzschild or even the Kerr space-time? I mean, is there a version of this decomposition in terms of the killing vectors? Because it's effectively spherical symmetry you're using, yeah.
Yeah, so here, so the killing vectors are sort of implicitly playing a role here. So, I mean, one killing vector that's not involved in any of this is the time-like killing vector. So I'm not in any of this, I'm not relying on the static nature of the background space-time, but I could use this and do a further decomposition in terms of, plane waves in time. I mean, I could do a Fourier transform and take out the time dependence through a Fourier transform. So that's an option that I would have that would be brought to us by that time-like killing vector. So I could use the static nature of the space-time as a means to do further decomposition, but I choose not to do that here. But there are two other killing vectors that are relevant here, and those are generating the symmetries on the sphere. So because everything here really relies on the spherical symmetry of the Schwarzschild spacetime, that's why all of this is useful. I'm really implicating here, although implicitly, the two killing vectors that are generating symmetries on the sphere, and that includes the phi killing vector that's generating motion around the z-axis. So that is involved in the construction of the spherical harmonics in that implicit way.
So I think there's a question. Sorry,
Yeah.
please go ahead. Yeah. Okay, so there is a question by Dhruv. I will just let him ask the question.
Yep.
Dhruv, you can go ahead and ask. Yeah. Dhruv, can you hear us?
Maybe you're muted.
No, I have unmuted him. I will just read out his question. He's asking,
Yep.
is there a difference in the capital dA, which you have used in tensor decomposition? I think it's the derivative, covariant derivative for the sphere.
Yep.
And del subscript A, which was used in defining XALM.
Yes. So when I was starting the, oh, sorry, which one?
Yeah, so I think I will.
Oh, yeah. So yesterday I was using the, let's see, when did I do this? Yeah, in any case, so if I were, I don't remember doing this, but I probably did. So yesterday I was talking about covariant derivatives in space-time. I could be talking about covariant derivatives in three-dimensional space. And here I'm just saying that this is a covariant derivative on the two-dimensional sphere. So that's the relationship. So you can always relate subdimensional covariant derivatives to higher dimensional, so you can go down from 3 dimensions to 2 dimensions if you want. So there are relationships between derivative operators, but I think it's simpler just to think of this as covariant derivative that is defined through a Christoffel symbol that's defined from this metric over here, the metric on the 2 sphere. So I think it's easier to think about it this way.
Yeah.
All right.
I think that answers the question, Professor Poisson. You can proceed.
Okay. Any more questions?
I don't see. There is one raised hand. Okay. Aditya, do you want to go ahead and ask?
Yeah, I'll just take a minute and ask my question. So right now you were talking about killing vectors of the Schwarzschild space-time, right? And you talked about the angular killing vectors and the timely killing. But right now what we want to look at is the metric perturbation, and they might not have those symmetries, right? So why are we talking about the killing vectors of the background metric?
So what I'm saying is that, so we're thinking of the perturbation, the perturbation tensor, the metric perturbation, as a tensor living in a background spacetime. And the nature of the background spacetime is what tells us what kind of decomposition is appropriate for that perturbation. So what I'm saying is that the killing vectors inform the way that I choose to decompose my metric tensor, my metric perturbation tensor, into the spherical harmonic bases that I'm defining here. So what I'm saying is that the symmetries of the background spacetime is informing the way that I choose to do all of this. And when I translate this into differential equations that these quantities will satisfy, the symmetries of the background spacetime will help me simplify the results and will take advantage of this decomposition. So the fact that I'm starting with Schwarzschild spacetime, which has that spherical symmetry, tells me that it's a good idea to seek an expansion in spherical harmonics. If I didn't have those underlying symmetries, if I didn't have a spherically symmetric background spacetime, chances are that a decomposition in spherical harmonics would not be helpful in any way. In different examples, if we wanted to do cosmological perturbations, the underlying spacetime would be homogeneous and isotropic. So if we considered a flat a universe with flat sections, we would use Cartesian coordinates, and we would find that the background metric would be independent of the Cartesian coordinates, and that would be a reason for us to seek an expansion not in terms of spherical harmonics, but in terms of plane waves, the e to the I kx type wave. So we would do a Fourier transform in x, y, and z, and that would reflect the symmetries of the underlying spacetime, and that would simplify, the calculations down the road. So that's how, the killing vectors enter, at least implicitly.
Thanks. That explained a lot. Thanks.
Okay, good. Okay, so let's move on. And I'm aware now that I'm introducing all sorts of technicalities, and that's a little bit the point. I just wanted to illustrate what goes into going from something which is very abstract and focusing on the main principles like we did yesterday, versus doing an actual calculation where you have no option but to delve into those technicalities if you want to do anything. And it's not necessary unless you really want to do this to become an expert at that. But I think it's good to be aware of what's required to turn the nice principles that we encountered yesterday and turn them into something very concrete. So let me just make a few remarks about what we've accomplished so far. So again, I'm using my language, which is not the cosmological language that we've talked about a little bit. We're focusing on how things behave on the sphere. So those guys, the spherical harmonics, they behave as a scalar. These guys behave as a vector. And these guys here, behaves as a tensor. And here I really mean a true tensor. And this is a true vector and a true tensor, as opposed to what we'll have down here, which are axial vectors and axial tensors. And language that is used in this context is that, well, we're talking here about even parity transformations because they have a certain behavior under parity transformation, which is just a mirror reflection across the origin. So that's often referred to as the even parity sector, those that come with those harmonics, or they're often in the literature, they're referred to as polar perturbations. So in the expansion that I had before, anything that comes with a y or ya or a yab, all of those things here would be considered part of the even parity sector of the perturbation. Apart from that, we also have the axial perturbations, the things that come with x's, either xa and xab. So this, as was pointed out, behaves as an axial vector because it was generated from a cross product. This is a tensorial generalization of this, so it's an axial tensor. And those behave differently from the y's under parity transformation. And in the literature, you'll see them as being described as having odd parity. So we're talking about the odd parity sector of the transformation. So all the coefficients that come in front of xa and xab that makes up the what's called the odd parity sector of the perturbation, or the axial part of the perturbations. So in a sense, on top of that spherical decomposition that we introduced, we also have a parity decomposition into even parity and odd parity. And that turns out to be also powerful because, as I'll describe in a minute, the perturbations actually decouple. So when you work out all the equations satisfied by all of those quantities, you'll find that there's going to be a set of equations that involve only even parity variables, and another set that involves only odd parity variables. There's no crosstalk between the two. And that corresponds to another underlying symmetry of the background spacetime that, that has to do with parity transformations. Okay, so that was just a bit of a reflection on what we did. I've talked about, at length, I've talked about the need to impose a coordinate condition to make everything well behaved, to adjust the coordinate freedom that we have as we go from the unperturbed spacetime to the perturbed spacetime. And yesterday we talked about the fact that this corresponded to different ways of making identifications between points down here and points up here. And we've talked about the fact that the freedom can be described in terms of Lie derivatives. So the difference between two perturbations, and here I'm talking about two metric perturbations. So I can define what I mean by a metric perturbation differently depending on what choice of identification that I make. But the difference between the two will always be a Lie derivative of the metric tensor. That's the metric tensor on the background spacetime. And it's always going to be characterized in terms of this four-dimensional vector that I'm calling big C over here. So, and big C can be thought of as being the shift in coordinates that I can make in the background spacetime to describe exactly the same perturbation. Now, the key point is that we always want to get rid of this gauge freedom. We want to, make a choice that hopefully will simplify the description of the perturbation. And here the freedom is complete. You really have to make judicious choices. Sometimes you have to be guided by experience and intuition, but one very popular choice of coordinate condition is what's known as the Reggie-Wheeler gauge, and that is when you simply put some of those metric coefficients to 0. So if I go back to the decomposition I had before, what I can do, what I can declare using the freedom that I have is to say that this can be set to 0 and this can be set to 0. I have the freedom to impose those choices, and if I do that, then yes, I will simplify the description because, I will kill degrees of freedom in the description of my metric perturbation. I will make it simpler. And also part of that freedom is the freedom to set H2 to 0. So that was the coefficient that lived in front of XAB down here. So I can dramatically simplify the appearance of the perturbation by relying on this coordinate freedom that I have. And we can do it this way by, imposing the Reggie-Wheeler gauge or Reggie-Wheeler choice of condition. Or, we can do it differently. In my work, I've imposed, different gauge conditions depending on different purposes, and I find some gauges more attractive than other. But the point is that we have the freedom to do that. We can do it, any which way. And basically it's up to us to find a gauge that suits our purpose, as best possible. So, and typically that means achieves the greatest simplification for a given problem. Okay, if you'll just allow me, I'm gonna, I have the sun in my eyes. I will just close my blinds. So, sorry, just give me a second. Okay, sorry about that. Let me go back to sharing screen. Okay, so right, so I've talked about the need to impose a gauge condition. So now, okay, so the goal is, remember what we're trying to do here. We're trying to describe the perturbation created by a small body orbiting a black hole, and I'm trying to do this. So I'm trying to step forward into this goal. So eventually, what we're going to have to do here, incorporating all of this, is to formulate the Einstein field equation. So we want to turn that into a big set of equations that each one of those coefficients that I've defined will be required to satisfy. So there's a big work needed to be done in order to turn that into a concrete set of equations. I can substitute the metric perturbation into the first order Einstein tensor and crank it out. And that requires a long computation, very tedious, very long, very, it takes patience to go through that. But what I will achieve in the end is, I will get a result from my Einstein tensor, my first order Einstein tensor, that will itself be decomposed into spherical harmonics in exactly the same way I described before, because these are, components of a scalar as far as the sphere is concerned. This is a vector on the sphere. This is a tensor on the sphere, and any tensor on the sphere can be decomposed in the way that we've described. Any vector on the sphere can be decomposed like this. Any scalar can be decomposed like this. So basically, using the completeness of the functional representation here, I can extract each one of those pieces of the first order Einstein tensor and set it equal to the energy momentum tensor of my moving point particle, which itself can be decomposed in exactly the same way. So basically what you end up doing here is to doing a lot of work, but in the end you have all the decomposed pieces of the Einstein field equations all decoupling from one another. It's still a bit of a mess of a system of equations, but you've decoupled them to the extent that they can be decoupled, and you've made the whole system a lot simpler than what it would have looked if you didn't rely on the decomposition. So lots of technicalities here, but the point is that those are all the smallest pieces of the Einstein tensor, and they give you the smallest pieces of the Einstein field equations that you can possibly achieve. So you really made maximal use of the symmetries of the underlying spacetime to, to construct all of that. And when you look at the practicum document, you will see all of those pieces worked out explicitly. So you will get all of that written out completely explicitly. All right.
Also,
so we're moving along. Yep.
No, I just wanted to check if you would like to keep the video off, or because we're not seeing
now
you.
I understand. Okay. I understand what happened. Okay, I didn't turn the video back on. Okay, sorry. Sorry about that. Yeah,
Sure.
so you were missing my face, and now I see that there's a lot of sun over here. So let me try to take care of that.
Dawood, there is also a hand raised with a question.
Yes, thank you, Shyam. I will just check it.
Yeah, so I'm back. So sorry about all of this. I'm actually quite happy to see the sun, but it's been interfering with my delivery here.
There is also a question, Professor Poisson, if you would like to. Yeah. So, Zakaria, you could go ahead and ask.
Yeah. Thank you very much. I wanted to ask actually, what is simpler, like taking the real equation and the Riccioli equation from the action or from the equation of motions, if one wants to do it analytically or using mathematics?
Oh, yes. So that's a very good question. So here I'm doing everything from the field equations. Because the field equations are tensorial, I have to, I have to work out the tensorial decomposition of the field equations. An option would be to start from the action. So I could start from the Hilbert-Einstein action, and I could introduce my metric perturbation in the action. Of course, the metric perturbation is tensorial, so I would have to introduce that decomposition in, in the action. But what I could do is to work on the action and simplify it to the fullest extent, so that the action in the end will be expressed in terms of simpler blocks than what I started with. And then I could vary the action and re-obtain my field equations that way. So it's a viable option. Some people find it simpler to do this, but it requires a bit of work because the action has to be worked out to second order in the perturbation in order to do anything useful. And that requires, perhaps a bit more work than to do it strictly at first order from the field equations. So I think there's a bit of a trade-off here to work with the action or the field equations, but in principle, this is all equivalent.
Great, thank you very much.
Okay, thank you for the question. Okay, so we're on our way to the calculation, and now I'm going to be a lot more schematic. So I'm going to say that in principle, we have the full set of field equations worked out. We have the smallest pieces of the first order Einstein tensor on the left-hand side. We have the smallest pieces of the energy momentum tensor on the right-hand side. We make them equal through the field equations. And now it's a matter of solving all those field equations simultaneously. And the task is made somewhat easier from the fact that all of the pieces decouple from one another. So you can work separately on the even parity sector. You can work separately on the odd parity sector. You can work separately for each value of L, each value of M, which means that all the subproblems become a lot easier than solving the full problems. But if you want to solve the full problem, of course, you have to, work through all the subproblems and then collect them all together. There are all sorts of results that have been obtained in the past to make the task even simpler in the end. So the main goal, as I said, would be to calculate gravitational waves that are emitted by a moving body around a Schwarzschild spacetime. And when you're looking at that problem, it turns out that you can package your perturbations into what are called master variables that obey very simple looking wave equations in now the reduced space, which has removed the angular dependence, because that's what the spherical harmonics were all about. And the reduced space then becomes two-dimensional, being spanned by the time variable and the radial variable. And when you do this, so for example, in the even parity sector, the master variable that was first obtained by Zerili is a combination of the K quantity we introduced before. It's a combination of HRR that we introduced before. And it's a construction like this. And if you package your variable in this way, you can find that this master variable obeys this simple looking equation with a potential function in the wave equation that is somewhat complicated, but looks like one of those potentials that you might encounter, for example, in quantum mechanics. And that's an equation that looks a little bit like a Schrödinger equation in quantum mechanics, especially after you get rid of the time dependence by taking the Fourier transform. That master equation, that master variable, will satisfy a wave equation with a source term that you can compute from all of those pieces of the energy momentum tensor. So that becomes a very efficient way of packaging the field equations. And there are results that tell you that if you know the solution to that equation, if you know the solution for the master variable, you can reconstruct the remaining metric perturbations from it. So that becomes very, very efficient and very useful. You can do it for the even parity sector. That's a picture of the potential that I was describing here. So it's a localized potential that goes to 0 at infinity, goes to 0 on the event horizon. You have this situation here. For the odd parity sector, you have another packaging of the variables. For example, the master function in this case is a combination of ht that we introduced before, hr we introduced before. And if you package it this way, you find that this master variable satisfies the same type of master equation as we had before, but with a different potential that looks a little bit simpler. And again, you have a source term for that master variable that can be constructed from the energy momentum tensor. So you have this very efficient packaging of the even parity sector of the perturbation, odd parity sector of the perturbation. And those two equations are very famous. One is Reggie Wheeler, this one. The previous one was the Zerilli equation. And those equations occur all over the place in the literature on black hole perturbation theory. That tends to be, the starting point of practical computations, especially when the goal is to calculate gravitational waves. And I'll come to that connection in just a moment. So, the Reggie Wheeler potential doesn't look very different from that. It's, slightly different, but qualitatively it looks exactly the same. Once you have those master variables, well, in principle, as I said, you can so if you have a solution for the master variables anywhere in space, you can reconstruct the full metric perturbation anywhere in space. There's an algorithm that allows you to do that. But if what you're mostly interested in are the gravitational waves at infinity, you can reconstruct the two gravitational wave polarizations.
Excuse me.
Sorry, let me finish the thought. So you can calculate the two gravitational wave polarizations directly from the behavior of the master functions at infinity. And when I say infinity here, I really mean the limit where r goes to infinity, but as a function of retarded time, where retarded time here is defined to be t minus r minus this logarithmic corrections that account for the delay, the gravitational delay that's encountered by gravitational waves as they propagate out of the space-time from the place where the source is to where you measure them at infinity. So what I'm saying here is that if you know the master variables, you can reconstruct the gravitational wave polarizations by just combining them evaluated in the right place and combining them with spherical harmonics with simple operations defined on those spherical harmonics. Right, so there was a question?
Yes, so when you showed us the Zerilli equation and the Reggie Wheeler equation, so now when we study quasi-normal modes, so there's a result that the Zerilli equation potential can be converted into the Reggie Wheeler potential. So we can solve just one problem and not the two problems separately. So
that's right.
That kind of simplification does not happen here for some reason, or are the two equations the same?
So yeah, okay, so the statement is that there's a transformation that you can apply to psi even, the master function for the Zerilli equation. There's a transformation you can apply to this that involves taking derivatives and doing various things that will transform this equation with the zero right-hand side to the Reggie Wheeler equation with the zero right-hand side. So if you do it in vacuum with no source, then the transformation the transformation gives you one, so basically tells you that only one wave equation, as you said, needs to be considered. The other one can be recovered. The solution to the other one can be recovered by that transformation. Now you can still do this in the presence of sources like this, but now you have to transform the source as well. And practically speaking, those transformations tend to be, not impossible, but a little bit difficult to implement. So what people tend to do in practice is to not bother with the transformation and just integrate both equations. Because if you know how to do it once, if you know how to deal with one numerically, it's very easy to just do it for the other one. So you don't have to change anything except for the identity of the potential. But one very nice aspect of this, and that's really relevant when the right-hand side is 0, is what you just talked about. If you're trying to describe the quasi-normal modes of a Schwarzschild black hole, you could have thought that there would be 2 sequences of modes, one for the even parity sector, one for the odd parity sector. But because of the existence of that transformation that takes one equation into the other, in fact, the modes for the even parity sector coincide with the modes for the odd parity sector. And the way that's usually described is to say that the spectra are, there's an isometry, so the modes are isospectral. Isospectral is the word I'm trying to say. But bottom line is that you don't have 2 sets of modes, you only have 1 set of mode because of that intimate relationship between the 2 wave equations. So that transformation is very powerful in order to establish this result. And I guess Chandrasekhar is the person who did the most to establish all of those really, really intricate results and relationships that you find in all of this. I mean, he really derived a lot of beautiful results about all of this. And he wrote a book that describes all of that. Does that answer your question?
Yeah, yes, thank you.
Okay, very good. Okay, so the point here is that the master functions give you direct access to the gravitational wave polarizations. So if your context is to calculate gravitational waves by solving the equations of perturbation theory, then for you, the master variables are, very, very useful. For the sort of things that I do, which is mostly about figuring out the tidal deformation of a black hole, when I work close to the black hole and not far away at infinity, for me, the master variables are not that useful. I prefer to deal with the metric variables themselves. And in my case, in my context, I don't see much benefit in dealing with master variables. But the point is that while they can be very powerful, they can be very useful, but it really depends on the context. Okay, I'll skip over this very quickly. That's just to say that, well, those equations that we've introduced here, the Reggie-Wheeler equation and the Zerilli equation, have the same mathematical structure. It's just that the potential is different in each case. And there's a very neat way of integrating this equation with a numerical algorithm that is based on null coordinates, the null combinations between t and the radial start coordinate, and so on. You can come up with a numerical grid in those coordinates, and you can come up with a very powerful algorithm that was devised by these people over here that allow you to do a numerical integration of those equations very efficiently, very very simply. And it's very easy, and there are codes out there that allow you to do that, to do those numerical integrations for a particle that moves in Schwarzschild spacetime, either moving on a circular orbit or an eccentric orbit. And that's finally all that you would need to do in order to really do this concrete calculation and obtain this result that I displayed before, that relates this motion in Schwarzschild spacetime to the gravitational waves that are produced. And those gravitational waves are being described in terms of the Zerilli function and the Reggie-Wheeler function. And that is something that you can obtain at infinity. So you're reading off the gravitational wave polarization at infinity by looking at your solution for those master variables at infinity. So the message here is that the theory that we worked out last time, I think, was very nice, very pretty, very conceptually pleasing. The nitty-gritty version of this, when you want to do something concrete, requires a lot of care, requires a lot of very intricate details, and you need to work through those if you want to do anything. And if it's part of your ambition to start working in black hole perturbation theory, you would have to go ahead and master those details, because no matter what you do, you have to face this in order to turn the nice principles into a concrete calculation that would allow you to achieve this. So in the practicum that I'll talk about in just a couple of minutes, in the practicum, you will see a version of this where I've done a lot of that decomposition work for you already, but now it's going to be your turn to go into the work of solving those field equations to describe a certain situation that's going to be different from that one. It will have to do with deformations of a black hole when you're focusing more on the vicinity of the black hole instead of going out to infinity. Okay, so let me wrap this up. I'll skip over those slides because I'm running out of time. I'll just say I'm just indicating here a bunch of references that if you look into them, they would teach you how to solve those equations either analytically or numerically. I'm also quoting some works from the literature where things were worked out by combining perturbation theory with Poissonian methods. So, I'll just skip over that and go over to the next part. And I think because I am running out of time, I will probably skip over this and leave that for you to read. I'll just advertise what I have over here. I have here, to finish up the course, I have here a very brief discussion of what would be required to generalize this discussion from Schwarzschild spacetime to Kerr spacetime. And that requires a different formulation, and it requires very different work because of the fact that the Kerr spacetime, unlike Schwarzschild, is not spherically symmetric. So all of those nice symmetries that we could rely on to do this decomposition that would for us achieve, the most simplicity, none of that is accessible in Kerr, none of that is available for Kerr. And we have to do things in a very different way. So the straightforward approach where you would take the metric, decompose it into a set of angular functions has been tried and has failed because no set of good spherical functions were found that would allow a nice decomposition, a nice decoupling of the equations. So you end up with a huge mess. The way out of this was formulated by Tucholsky very famously in the early 70s, where he found out that if you're using the Newman-Penrose formalism and deal instead of metric perturbation, if you deal instead with perturbations of the Riemann tensor, then you can achieve simplicity in a very different way. And I won't go into the details of this because, again, I'm running out of time. I'm just saying that while you start with a Kerr spacetime, which is very complicated compared with Schwarzschild, you introduce a basis of null vectors in that spacetime. You take projections of the Riemann tensor. Here I write it as a C because the Riemann tensor is identified with a Weil tensor. When the Ricci tensor is 0 in the background spacetime, the two tensors are the same. But basically, this is the Riemann tensor that's being projected against those null vectors. So you decompose in a vector basis like this, the Riemann tensor into scalar components. And what Tucholsky worked out is that the perturbations that are described by either psi naught or psi 4, those particular components of the Weil tensor, those turn out to be described by equations that decouple from one another, and also equations for which you can apply separation of variables strategies to solve them. So for those variables, you can actually introduce a nice set of angular functions that allow you to separate the variables and end up with equations that can actually be dealt with in a reasonable manner. So that was a beautiful thing. And here I didn't have the time to go into any details of this. I'm giving you a guide to the literature on this if you're curious. And what I want to, and that's the the essential of what I wanted to say about Kerr. And before I really close off for the day, let me just say one word about the practicum. So what I thought you should do tomorrow, instead of me lecturing, let me share a different screen. This. Sorry. Find my, okay, so you see this document over here?
Yes, we can see.
Okay, so so instead of me giving another lecture tomorrow, I thought it would be a lot more useful for you and a lot more effective if you were doing the work instead of me doing the work, and carried out a practical exercise as opposed to keep on listening to me droning on about decompositions and various things. So I could have continued to lecture, but I think it's going to be a lot more effective if you go through a practical exercise where you will solve the perturbed Einstein field equations to calculate the deformation of a Schwarzschild black hole under the action of a tidal field. So what I provide for you in this practical document is a full listing of the perturbed field equations. So this is the full content of the Einstein, the first order Einstein tensor, fully decomposed in a way that I described before, in terms of all of those metric perturbation variables that we introduced. So I provide all of that for you, and then I provide you with guidance on how to solve the field equations to describe that deformation of a black hole under a tidal field. And before I task you with doing all of this, I give you some background knowledge, some background motivation from Newtonian theory that will identify the task and identify the goals of the practical exercise. So what I would like you to do here is to take the time tomorrow to go through this. I don't think you'll be able to complete all of this in the 1 hour and a half that's at your disposal tomorrow, but you should be able to get started on this. And hopefully you will be motivated enough to keep on going and complete the practical exercise and see much more intimately and much more practically what's involved in doing that kind of work. And I think that will be very good for your education, and certainly much better than continuing to hear me lecture about these things. And what I thought I would do tomorrow is to give you about an hour to get started on this. And I will sign on after that hour and ask if there are questions. And if there are no questions, then I'll be happy to keep you working at it. But if there are questions, I'll be happy to answer them and hopefully clarify the tasks that you have to face to complete the work here. So that's what I thought I would do tomorrow. And that, I suppose, completes my lecture for today.
Thank you, Professor Poisson. There is one question in the chat box concerning, I think, the last part of your lecture today.
Yep.
I will just ask the question because I think the participant is having some issue with the audio. So the question is that there is a master variable construction in cosmological perturbation theory, which gives you the so-called Bardeen variables.
Yep.
These are constructed in a gauge invariant manner. So my understanding of the question is that, is there a similar consideration that has gone into the construction of the variables you described in terms of the wild tensor towards the end? You described certain master variables, right? In terms of
so the so in the Schwarzschild case, the master variables that we talked about, the Reggie Wheeler and the Zarili functions, are analogous to what you would get in cosmology in terms of the Bardeen variable, and there's also a Mukhanov-Sasaki variable that people use. Those are similar constructions that are that also have this property of being gauge invariant. So you can construct those things from different gauges and they still are the same quantities. And for Kerr, the Tarkovsky variables, the psi naught, the psi 1, psi naught and psi 4, can be thought also as master variables that also share the property of gauge invariance. So in that sense, there's analogs between all of those things. I mean, they're not exactly the same thing, but they're basically achieving the same purpose, which is to package metric perturbation variables into something that has the property of gauge invariance, and therefore means that you can relate them to different metric variables in different gauges, and that's useful.
Thank you, Professor Poisson. I think that answers the question. Is there any other question for today's lecture?
Dawood, there are a couple of hands raised.
Yes, yes, I just noticed it. Thanks, Shreya. Shubhadeep, you want to go ahead and ask your question?
Yes. So I have a question about that numerical integration scheme that you showed.
Yep.
Yeah. So that I think that is the method that was pioneered by Gundal, Pulin, Price, right? Uh,
Yes.
uh, so the thing is that so in that problem we don't actually specify boundary conditions. Instead, we sort of just specify some initial data on the null surfaces. Uh,
That is
so
correct. Yep.
I actually don't understand this, but if we don't specify boundary conditions explicitly, then how do we recover, say, the quasi-normal modes or the, that from the waveform? Like we are sort of sidestepping the question of imposing boundary conditions on it, no? And
Right. So yeah. So that's a very good question. So how you choose to impose boundary conditions or how you choose to impose initial conditions really depends on the problem. So if your goal is to calculate quasi-normal modes, what you would want to do is to first impose a form of solution that's given as e to the minus I omega t, and you would make omega complex, and you would look for a solution like this. And then you would look for a solution that corresponds to incoming waves at the horizon and outgoing waves at infinity. So to define a solution that describes a quasi-normal mode, you would want to make explicit use of those boundary conditions. In the context I was describing, where you have a body moving in a Schwarzschild spacetime, the type of problem that I was considering here was an initial value problem instead of a boundary value problem, because I wanted to say, let's start with a known situation at t equals 0, and let's see what we get as time moves forward. So we have to impose initial conditions. In principle, we would have to enforce conditions of outgoing waves at infinity and incoming waves at the horizon. But the beauty of the numerical methods that I described is that by formulating things on null cones, as I have, we can impose initial conditions on the initial light cone. And after that, everything is taken care of. There's no need to add any more boundary conditions to the specification of the solution. It's guaranteed, those initial conditions are guaranteed to produce a unique solution. So the formulation of the problem, of course, depends on the context and depends on exactly what you're trying to achieve, and you have to do things differently depending on how which problem you're trying to solve.
Another thing is that basically, so since u and v, the null directions are sort of the characteristic directions of the wave equation.
Right.
So we can impose initial data independent of each other, right? So
on the two null surfaces, that's right.
Yeah,
on this branch
so
and
we
on
can
that
have
branch.
so we can have Gaussians on each of them, or are there some physical considerations that go into selecting the initial data on the surfaces?
In this case, no. So in this context, because the wave equations are very simple, as you pointed out, we have free data here, free data there, and there's no, there are no constraints to be satisfied. If we were working on a Cauchy surface, a t equal constant surface, we would have to make sure that the initial data satisfies the constraint equations of general relativity. And that would mean that we're not free to specify anything we want. But in this characteristic formulation, we are. So that's another advantage of the characteristic formulation, in that we are free to impose this data. So it's a rather nice property of this.
And just last question, you mentioned that there are some standard codes that do this. So I have been writing my code, so it would be easier. So if you can give a reference to some existing codes that are used.
Yeah, so the best resource for this, it's called the Black Hole Perturbation Toolkit. And if you Google that, I'm sure you'll find the website. So it's a database of codes that have been maintained by various people, mostly working on self-force. Probably the reference that I showed you at the beginning of the lecture by Pound and Wardell, I think it probably has a reference to this. But yeah, I mean, there's this thing called the Black Hole Perturbation Toolkit that contains all sorts of codes, I think mostly formulated in Mathematica, that allows you to do all sorts of things like integrating the Tarkovsky equation. And, you know, there's really a lot of very useful resources there that you can, you know, you can use. It's free, you know, it's free access.
Thank you. Thank you.
So there is another question by Zakaria. Zakaria,
Thank you.
Go ahead. Yeah, please go ahead.
I was asking about the Reggie-Wheeler gauge, because I thought we use it only to obtain a Reggie-Wheeler equation, but it's not. So what is the simplest way to get a Reggie-Wheeler equation? And is Reggie-Wheeler gauge the most favorable one to use it? And the second question, it's about using perturbation theory for MREs. Because I know that we don't need quasi-normal modes, but what is the most adaptable formalism to get equations of motion and so on, and how we can use perturbation theory?
Okay, okay. So the first question had to do with the Reggie-Wheeler gauge. So it's certainly true that if, you know, if what you want to do is to derive the derive the Reggie-Wheeler equation and derive the Zerili equation, the most efficient way of doing it will be to impose the Reggie-Wheeler conditions. And that simplifies, I think, to the largest extent possible, the appearance of the perturbation. And that allows you to carry out those manipulations that will give you Reggie-Wheeler and Zerili in the most effective way. So if that's the purpose, then I think that's, you know, that is probably the best choice of gauge. There are situations where I found it useful not to use the Reggie-Wheeler gauge, because there's something a little bit strange in the Reggie-Wheeler gauge, in the sense that if you're looking at what happens at infinity, the gauge is such that your metric variables are not decaying at infinity, but they tend to approach a constant at infinity. So the way we say it is that the gauge is not asymptotically flat. And that's not necessarily a problem, but, you know, sometimes when you want to calculate things, it's something that, you know, can be a bit of a nuisance. And I found it useful to consider other gauges to do that. And one gauge that I particularly like is one that is defined on null cones and gives you a geometrical meaning for coordinates you would use on null cones. So again, the point is that choices of gauge is really a matter of taste and a matter of convenience, and different problems would call for different, you know, choices, you know, as a matter of convenience or as a matter of preference. But there's really nothing more to it than that. Your second question had to do with how to calculate gravitational waves from MREs. Was that the question?
Yeah, it was about MREs, using perturbation theory of black holes for MREs.
Right. Yeah. So what about that? Sorry. What
Yeah,
what
how
are you
to use
asking?
perturbation, because I know that we can use Reggie-Wheeler and Zerili equations for MREs. Even we are describing in spiral, not a ring down. It's a different part of the signal, but we are using the same formalism instead of using post-Newtonian regulation.
Yeah. I mean, the problem I was describing, where I had a small mass going around a black hole, well, that's an MRE problem. And what I was describing is the first order implementation of the MRE problem, where at first order we can figure that the particle keeps on the same orbit forever. That's, of course, not what happens in reality. But once I've calculated the gravitational waves coming out of that motion, I can look at infinity and see how much energy was lost to gravitational waves, how much angular momentum was lost to gravitational waves. I can look at those losses on the horizon, and then I can infer the changes on the motion that come about because, you know, the orbital motion has lost energy and angular momentum to gravitational waves. So I can go from this first order formulation into an implementation where I include losses into the description of the motion. And that's a, you know, a sort of bootstrapped way of describing the MRE problem, where we start describing the in-spiral. So it's basically just continuing on that theme that I explored in today's lecture.
Is there a limit on the mesh ratio that you consider, like from which limit you can consider a system as an memory or not?
I've talked about that in my first lecture. So I've talked about you know, the relationships between different perturbation methods as a way of testing out accuracies of perturbation you know, strategies. And there's no hard limit on how small the mass ratio must be, but you can sort of play a game of comparison and decide, for example, if a 0.1 mass ratio is too large for the type of accuracy you want to achieve, or whether 0.01 or 10 to minus 3. So basically, it's really a matter of deciding how much accuracy you want, and asking, given this accuracy, how large a mass ratio can you tolerate to achieve that accuracy? So there's no hard limit. There's no hard answer to that question.
Okay, great. Just about the reference. So to derive the Ritchie-Wheeler equation, for example, by hand, is the first reference that you recommend good for that, and also for MAs? Like the first review that you recommend?
Yeah. So that review by Pound and Wardell, I think that's probably the best resource to find anything you want to know about perturbation theory. And if it's not done in the paper, they will have references that shows you everything. So you can really start there, and I think you'll be well served.
Thank you very much.
Okay. Are there? I don't see any other questions. So if there are no further questions, let's thank Professor Poisson again.
Daud Chandra has a question.
Oh, okay.
Sorry for the yeah. So very quickly, Professor Poisson, I saw the Ryuichi's calculation of 44 PN order.
Yeah.
Does it affect our concerns about numerical accuracies? I mean, how these high PN order calculations affect our concerns about numerical accuracies and so on? I mean, we are going so high to high post-Newtonian orders and so on.
Yeah. So what Fujita achieved there is just mind blowing. I mean, it's incredible that he was able to push the calculations to such a high order. What this achieves, though, is to inform us on what we're missing. I mean, in the context of very small mass ratios, it tells us about what we're missing when we push a calculation, for example, for comparable masses up to 4 PN. I mean, that's the current state of the art, to calculate the equations of motion to 4 PN and eventually achieving the gravitational waves at 4 PN. So we know that when we calculate to 4 PN, we leave out everything else beyond. But when you compare those results with Fujita's results that has everything, then you can use that to measure the error made in what you left out. And basically it tells us that, well, 4 PN is probably it's probably accurate enough. So basically it's a way of gauging the results, the errors in the methods that are made. I see that Guillaume is in the audience. I'm sure Guillaume would have a lot more to say about this.
It's very important for us also to check the validity of the algorithm, not only just for accuracy purposes, to be able to compare, and then also to build EOB models. It can be useful to have further coefficients. You can put them together into things that try to make to gather information from several sources. So yeah, it is definitely it was an amazing result and very interesting for us.
Yeah, in fact, one aspect that I found the most fascinating in all of this, that's been a constant theme over the last 20 years, is how powerful it is to combine different approximation methods and inform one method from results from another. There's been a lot of nice, work on combining different approximations, sometimes just for, as Guillaume said, to validate the ideas and the results from one approximation method by using results from another, but often very pragmatically to try to construct something even better than each one separately by combining results from many methods. You can really package them in a really nice pragmatic way to actually get something that in the end will be more accurate than any one method separately. That's what Guillaume meant by the EOB methods, the effective one body formulation of all of this, where you really try to import information from all possible directions into one uniform, combined package.
Right. But the question was also about, when we are looking at a term like at 44 p.n. order, we are looking at powers, V by C power, 44. And,
right.
Then we are looking at accuracies or, which are much smaller than the machine accuracies. So I was just wondering, whether the coefficients, these coefficients, how we are assessing their importance and things like that at that level. So whether there is a parallel exercise to understand these corrections and so on.
Oh yeah, I mean, there's been a lot of discussion to this, and of course the size of the the size of the last term in that series in powers of V over C will depend on the value of V over C. So if V over C is 0.1, then of course 0.1 raised to the power of 44 is going to be hopelessly small. No one cares about it. But if V over C is 0.5 or even beyond, approaching the speed of light, then those higher order corrections can actually start being being important. And if, for example, you were to compare this to a numerical relativity simulation, you could really say, something meaningful about the accuracy of each method. So, I mean, it was a sort of feat of strength to go all the way to, it's not actually 45 Poisson-Newtonian orders, it's actually 22 because,
correct,
the Poisson-Newtonian ordering is V over C squared.
Right,
I mean, it was a feat of strength to go all the way. I don't think I don't think there's going to be all that much practical use out of the, the terms beyond, 10 Poisson-Newtonian orders or something like that. But still, I think as a matter of cross-validating different approaches to understand the structure of log terms, for example, I mean, to understand the formalities of all of this, I think it was a very useful thing to do. And again, in order to also validate different approximation methods, it was something very useful.
Right. Thank you so much. Yeah.
Okay, are there any other questions from the audience? If not, let's thank again Professor Poisson for the lecture, and we'll meet again for the session tomorrow. As is indicated, it's a practical session, and Professor Poisson will join in an hour's time to check if there are any questions and discussions.
And the file will be made available somewhere down?
Yes, it's already been made available on the web page.
Okay.
It's already on the web page. Yeah. So if the participants have not noted it, the file which was given by Professor Poisson has already been uploaded on the school website.
Thank you.
Okay, very good. So thanks again for your attention today. Thank you very much for the questions. And good luck with the practical exercise. And as was just mentioned, I will show up at, 6:30 your time, and I will see if there are any questions. And I'll be happy to answer whatever I can. And but the main goal is for you to do the work and learn firsthand how to do calculations along the lines that I've described today.
Professor Poisson, would they need a specific tool to do these, or it can be done by hand?
So in principle, it can be done by hand. I mean, there are some equations so there's going to be some differential equations that will require solutions. So in principle, it could be done by hand. If you have access to Mathematica or Maple or other symbolic manipulators like this, by all means use them. I mean, use all the tools you have at your disposal. This is not an exam. I'm not testing anything. So whatever is at your disposal, make use of. But in principle, you could do everything by hand. Those calculations are accessible to hand techniques.
Okay, thank you.
Thank you. Have a good day, Professor Poisson.
Okay, so have a good evening, and we'll see you tomorrow.